Now that we've completed our introduction to Newton's three laws, the first, the law of inertia, the second, the net force is equal to the mass times the acceleration, and the third, the law of action and reaction. We now reach the point in the discussion where we want to apply Newton's laws to the solution of actual problems. This is that moment in every physics lesson when it goes from being metaphysical and philosophical, conceptual, to being actually practical. So today I'm going to be demonstrating for you the skills that I expect you to have. At some point, you have a test or a quiz, and on that, you'll be expected to solve Newton's second law problems. Just like our kinematics problems, I've devised a strategy that hopefully give you the best opportunity for success at solving such problems. There are many, many different kinds of Newton's second law problems. The one that I'd like to start with today is one that is relatively simple. As we go on with our study, we'll make things a bit more complex as we go. One issue of complexity is Newton's second law is a vector equation. The sum of the vector forces is equal to the mass times the vector acceleration, which means that Newton's second law is an equation in 3 dimensions. So things can get fancy indeed. But what I'm going to do now is restrict myself, just for the moment, to solving a problem of 1-dimensional motion. That'll greatly simplify the approach. Nevertheless, the fundamental approach that I'm about to do is the approach to every Newton's second law problem, no matter how sophisticated. So while the solution to the problem that I'm going to solve is itself interesting and a classic problem that students are often asked to solve, I ask that as I go along, you pay careful attention to my description of the procedure that I'm following in order to get answered. Procedure is always the same. Consider this situation that I've drawn here on the board. I have an elevator, which is just a box with a cable, that can draw the elevator up and down in a building, an experience that all of us have had, including our friend Slim, who stands here now in the elevator. Now, Slim is curious because he's observed something when riding elevators that we all have. There's a moment on the elevator when I get on, I stand on the elevator, and I press the button for a higher floor. And as the elevator begins its motion, I suddenly feel heavier. There's a brief moment when there's a little bit of an oomph and I feel more weighty in the elevator. But then the elevator approaches constant speed, and the experience of being on the elevator is like the experience of just standing in any room, even though the elevator is in motion. And then as the elevator approaches the destination floor, at that instant when the elevator accelerates to a stop, suddenly we feel light at that moment. So Slim is curious. He wants to find out if when he's riding on the elevator and he feels heavy, and again riding on the elevator feels light, he wants to find out, is he actually heavier or lighter? Because Slim knows that in the morning when he goes into the bathroom and stands on the bathroom scale, many of us have them, we stand on the bathroom scale, it has a display on it that reads his weight. Slim has a mass of about 60 kilograms. That's an assumption I'm making. It's slightly less than the average mass of a human being, but then again, Slim is a stick figure, so it probably makes sense. That is Slim's mass. It's a measure of his inertia. It's a description of his resistance to acceleration. It is not his weight. Slim's weight is the force of gravity acting on him, which is his mass multiplied by the acceleration due to gravity, which we know is 9.8 meters per second squared. Not positive, not negative. When I see the symbol G, it is 9.8 meters per second squared. For the purpose of simplifying my calculation in this particular problem, I'm going to say that 9.8 meters per second squared is approximately 10 meters per second squared. I wouldn't want to use that if I were solving some sort of engineering problem or if lives were at stake. But since this is just an imaginary physics problem, I'm going to make that approximation. Immediately, it's nice. Because if Slim's mass is 60 kilograms and the acceleration due to gravity is 10 meters per second squared, that means that Slim weighs 600 newtons. Perfectly appropriate weight for a person. So when Slim weighs himself in the morning on his bathroom scale, it reads 600 newtons. So he picks the scale up and takes it with him to the elevator. So we see in my drawing here, Slim standing on the bathroom scale in an elevator. And that is the first step of my problem solving, just as it's always been. The first thing that I do is I draw a picture that represents the physical situation that I'm trying to solve. And there it is. Second step, same as always. choose the coordinates for solving the problem. If I'm talking about Newton's second law, then I'm certainly considering the acceleration, which is related to the velocity, which is related to position, and none of that has any definition without coordinates. So I'm going to choose, for my purposes, upward to be the positive direction. And that's not surprising because the elevator is going to go up. The elevator might also come down again. It doesn't particularly matter the direction of the motion. When I choose upward to be the positive direction, what I'm doing is I'm deciding that forces that act upward are positive forces, and forces that act downward are negative forces. That's the reason for the choice, because force is a vector, and without a sense of direction, then I don't get that vectorness in my solution. And things work out wrong for me. So I've drawn a picture and I chose my coordinates, and now it's time for me to get my information organized. When I solved kinematic problems, what I did was I made a list of the known kinematic quantities just to get my organizing done. When it was a two-dimensional problem, I made two lists. I mentioned at that time, when we were learning to do that particular technique, that all of the thinking happened on the lists. That all of the physics happened when I was considering what quantities were known, unknown, what their units were, signs, all of that particular information. The list was where the physics happens. Well, when I'm solving a Newton's second law problem, all of the thinking happens, all of the physics happen when I draw my free body diagram. So the next step in my problem-solving strategy is to draw a free body diagram. What do I draw a free body diagram for? Choosing what to draw the free body diagram for is like choosing a coordinate system. It is completely arbitrary. You draw a free body diagram for whatever you want. You want a free body diagram for the elevator and the building that it's in? Then do that. You want a free body diagram for Slim only? Then do that. You want a free body diagram for Slim and the bathroom scale and the earth and all the change in Slim's pockets? Feel free. You draw a free body diagram for the object whose motion you would like to understand. In this case, I would like to understand the motion of Slim. And so I'm drawing a free body diagram for Slim. It's important because on my free body diagram for Slim, I'm only going to draw those forces which act on Slim directly. It's possible when I'm solving a problem that the object of interest might be exerting forces elsewhere. I'm not interested in those forces. I'm only interested in the forces that affect the motion of Slim. Now, I may be a little inexperienced with what kind of forces act in what situations. I won't really get the hang of it until I've solved lots and lots of problems. So I have a list of forces that I can go down. That list of forces appears in your notes somewhere. I'm going to run down it now. Starting at the top of my list of forces, I ask the question, does Slim have weight? The answer is, of course, yes, he does. It's the whole issue. And so on the free body diagram that I draw for Slim here, which is just a box that sort of implies Slim as an abstraction, just a box, I draw an arrow downward, and I label it mg, the weight of Slim. I know that Slim's weight is 600 newtons. I don't tend to write numbers on my free body diagrams, though. I think it's vulgar. So I write the symbol that I know stands for weight, mg. Weight is calculated as the mass of a thing multiplied by the acceleration due to gravity near the surface of the earth, g. So mg, the weight of Slim, directed downward. By the way, because I chose upward to be the positive direction, that immediately means that this force is a negative force. And that's okay, no problem. But it's good that I recognize that. Is anybody pushing and pulling on Slim? Nobody pushes Slim around, but also there's nobody inside the elevator with Slim to exert extra forces on him. There's no extra nonsense going on. So I don't have any push-pulls going on Slim. Any ropes attached? I see heads not nodding up and down, not going back and forth, but sort of going around in circles because the elevator is supported by a cable, isn't it? And that cable has some tension in it, a force of tension. But here's the thing. Does that force act on Slim? No. If you come to the elevator and the door's open and there's just nooses hanging there, take the stairs. It's not how an elevator is supposed to work. The force of tension in the cable does not act on Slim. So I do not include it in the free body diagram. So there's no tension. Are there any normal forces? Sure. Slim is standing on the bathroom scale, so the bathroom scale exerts a force upward on him perpendicular to the bathroom scale. The word normal means perpendicular. Normal force is the force of contact, and that contact force on Slim points directly upward. Are there any friction forces? Well, when it comes to friction, it turns out it's not going to influence the problem. Because there Slim stands in the elevator. The forces that cause him to move are the normal force and the gravitational force. What does friction matter? Well, as it happens, it does. As I stand here in the front of the room before you, I'm relying on friction to stand. Were it not for the friction forces between my feet and the floor, I would do a split. My feet would accelerate away, and I'd do a split and probably cry out loud, and then fall over backwards, and then drift along the frictionless floor until I hit a wall somewhere. I rely on friction to stand. So on my free body diagram, I've added a little bit of friction to the left and a little bit of friction to the right just to help Slim stand. But notice, those two forces are equal and opposite to each other. They add up to zero. And it doesn't really matter at all because the motion is vertical. It's not horizontal. In this problem, the horizontal acceleration is zero. So the horizontal velocity is zero. So the horizontal displacement is zero. It's completely uninteresting. The vertical is where the action happens. But we'll include those little friction forces in there just for the sake of completeness. Are there any springs in the problem? No. And there are a lot of other forces out there, but these are the ones that I choose to consider in my physics. And really, the other ones that we threw on the list is like maybe forces where viscous drag, but he's in an elevator. The air moves along with him instead of him moving through the air. So there wouldn't be viscous drag anyway. He doesn't have a jetpack on, so there's no thrust. He's not in liquid, so there's no buoyant force. All these extra forces, there's none of that going on. This is a really good free body diagram. For Slim's motion when he's standing on a bathroom scale in an elevator, I have drawn a picture. I chose my coordinates. I drew a free body diagram organizing all the forces. And that free body diagram is a big help to me because what I do next is I apply Newton's second law to my free body diagram. I apply Newton's second law to my free body diagram. Sigma F is equal to ma, the sum of all the forces. The free body diagram is necessary because in any given physical situation like this one, there could be more than one force acting in many different directions. The free body diagram helps me to write the net force. Again, that Newton's second law equation is three-dimensional. I only need it to be one-dimensional. So I could, to clarify this for anyone who is reading my problem solution, I could write sigma F equals ma as the sum of all the forces along the y-axis, because we all generally agree that the y-axis is the vertical axis. That's how we learn our mathematics. That the sum of all the forces along the y-axis is equal to the mass times the acceleration along the y-axis. That is, write Newton's second law for the vertical motion only. And as such, when I write the net force, the sum of the forces, I want to consider only those forces that act along the y-axis. Look at my free body diagram. Which are they? The normal force and the weight. The normal force is a positive force because it points upward in the direction that I've chosen to be positive. The weight force is a negative force because it points downward in the direction opposite that which I chose as positive. So when I write the sum of the forces, I like to lead off with positive terms if I can, as a purely aesthetic choice. I'm not wild about equations that start with a negative sign. I think it's icky. So I'll start by writing the normal force, which is positive, minus mg is equal to ma. Shadi, why did you say minus? It's the sum of the forces. Well, yes, it's the positive normal force plus the negative weight force is equal to the mass times the acceleration. I put a box around this equation because it's called the equation of motion for Slim on an elevator. A couple of details about that. This equation is the solution for Slim on an elevator. It's not the solution to every Newton's second law problem ever. When I studied kinematics, I was spoiled a bit because I derived 3 kinematic equations, and I could put them over here on the right side of the board and say every problem is solved with these 3 equations. Newton's second law problems, it doesn't work that way. In Newton's second law problems, you create your own custom equations from your free body diagram that solve that specific problem. So this equation, here in the box, is the equation of motion for Slim on an elevator. It works for all states of motion of Slim. It works when Slim is at rest. It works when Slim moves with constant velocity. It works when Slim has a positive acceleration. It works when Slim has a negative acceleration. It works all the time. It's pretty fantastic. It's a remarkable achievement. Now, that is my Newton's second law analysis, and I do that every time, every problem that I solve. When I finally get to the point where I have my equation of motion, it's time to ask a question. Well, Slim's question is, what will the bathroom scale read when I get on the elevator? So Slim's careful experiment is he puts the bathroom scale down on the floor, he stands on it, and he presses the up arrow, and he looks to the scale to see what it will read. We use a bathroom scale to measure our weight. Everyone knows that that's what it's for. And when you step on it, your expectation is that it will read your weight. Well, I have news for you. It doesn't read. The bathroom scale doesn't know anything about the force of gravity and the motion of the planets and the nature of gravity in our cosmos. You bought it at Target, for crying out loud. What a bathroom scale does read is when you step upon it, the force that it must exert upward on you. The bathroom scale doesn't read your weight. The bathroom scale reads the normal force that it must exert on you. It does so mechanically using springs or electrically piezoelectric crystal, but it measures the amount of force that it must exert upward on you. The bathroom scale measures the normal force. So I'll take my equation of motion and solve it for the normal force, because the normal force is what it will read. Now, when the bathroom scale is sitting at home in Slim's bathroom, the acceleration of the bathroom is equal to 0. I think you will all agree that the acceleration of your bathroom is 0. It makes it easier to use the bathroom. Well, I've got a little bit of extra news for you just as an aside. The acceleration of your bathroom isn't 0, because your bathroom is in your house, and your house is on the surface of the earth, and the earth is rotating, and so your bathroom is going around in circular motion as the earth rotates, and the earth is orbiting the sun, and along goes your bathroom with it, and the sun is orbiting the center of the galaxy, and the galaxy is zooming off into the void of the cosmos. So the acceleration of your bathroom is not 0, but it's very small. Otherwise, you'd be hanging on for dear life. The acceleration of the bathroom is very small. Let's just call it 0. If the acceleration is equal to 0 when Slim steps on the bathroom scale at home, what does this equation predict? Well, if the acceleration is equal to 0, then the first term no longer appears, and the normal force is equal to mg. The normal force is 600 Newton. The normal force is equal to Slim's weight. And so a bathroom scale can effectively be used to measure the force of gravity on Slim, because when the acceleration is equal to 0, the normal force is equal to the weight. Not just that. If Slim and the bathroom scale together are moving at constant velocity, that's also acceleration is equal to 0. That also is acceleration equal to 0, and the bathroom scale also measures the weight. Now, when I ride on an elevator, I push the button to go to a higher floor, and the elevator accelerates. But not the whole time. It accelerates for a bit, and then it moves at constant speed. And then when it arrives at the appropriate floor, it accelerates to a stop. You've already solved this as a kinematic problem. An elevator speeds to a start, moves at constant speed, and then accelerates to a stop. In that middle bit, it's moving at constant speed. So when Slim's standing on the elevator and the elevator is moving upward at constant speed, he looks down and it reads 600 Newton. It reads the normal force that the scale is reading on him, which is coincidentally equal to his weight. But now the interesting part. Slim takes the scale and he puts it on the elevator and he stands on it and he pushes for an upward floor. Now, upward the positive direction, velocity of the elevator is 0, but then becomes positive and more positive as it goes up. It's a situation of positive acceleration. And also, by the way, a situation where Slim feels heavy. Imagine that the acceleration is positive 2 meters per second. I'm just making that up. What does the scale read? Well, the scale reads the normal force. The normal force is equal to the mass of Slim multiplied by the acceleration, plus the mass of Slim multiplied by the gravitational acceleration. So, Slim's mass being 60 kilograms multiplied by 2 meters per second squared, that's 120 newtons of accelerating force. Plus 600 newtons of Slim's actual weight. The scale reads 720 newtons. As Slim stands there, pushes the button to go up, when the elevator accelerates, he looks at the scale, and the scale goes, whoa, and increases to 70 newtons, validating Slim's feeling that he has become heavier. Is he heavier? Is the force of gravity on him greater? No. The force of gravity is still 600 newtons. Slim's weight has not increased. Slim's weight appears to have increased. And so very often, and you may find this in your problem solving, The normal force in this circumstance is referred to as the apparent weight. His weight appears to be larger because the elevator has a positive acceleration. There are two ways that can happen. The elevator can have a positive acceleration when it is going upward and speeding up. The elevator can have a positive acceleration when it's going downward and slowing down. And these are the two circumstances in which, from your own personal experience, feel heavier. The apparent weight is larger. Now, what if the acceleration of the elevator is negative? When does that happen? When Slim is going upward in the elevator and arrives at the destination floor, he feels light for just a moment. That's a situation where the acceleration of the elevator is negative. Imagine that it's negative 2 meters per second squared. Doing this calculation for the apparent weight is ma plus mg. That's 60 times negative 2 is now negative 120 plus the 600 newtons of Slim's weight. The scale will read 480 newtons. The scale will read less than his weight. As he arrives, cruising at constant speed, it reads 600 newtons, and as he arrives and the elevator slows to a stop, the scale will dip to 480 newtons, implying that he weighs less. He doesn't weigh less. He still weighs 600 newtons. The apparent weight has become 480 newtons. Feel lighter. Just for fun, take it to the extreme. We cut the elevator cable and allow the elevator to free fall under the influence of gravity. And under those circumstances, upward chosen to be the positive direction, the acceleration of the elevator is negative 9.8 meters per second squared, or in this case, negative 10. What does the scale read then? Well, since the apparent weight is the mass multiplied by the acceleration plus the mass multiplied by g, it's 60 times negative 10, which is negative 600, plus 600 is 0 newtons. The scale reads 0. Slim's apparent weight becomes 0. What is the experience for Slim inside the elevator? Free fall, which is Slim floating in the elevator like an astronaut. And he can do amusing things like just do backflips and flip over and over. He can eat jello in amusing ways, swimming through the air. It all works out great until the elevator reaches the bottom of the elevator. Slim is a stick figure, though. He doesn't have the same issue, mortality, that you and I have. Been doing physics for 25 years and doing just fine. But he appears weightless. He's not weightless. The force of gravity on him is still 600 newtons. It was 600 newtons the whole time. He appears weightless. Just like the astronauts who inhabit the International Space Station. We've all seen videos of astronauts in space station having a good time, flipping around and floating, weightless in space. The mistake is often made to suggest that this happens because there's no gravity in space. That's not true. Think on it. If there were no gravity, then the International Space Station would obey its natural tendency and it would travel with constant velocity in a straight line forever and ever. Bye-bye, International Space Station. Fly away. But it doesn't. The force of gravity curves the International Space Station into orbital motion. The astronauts inside the International Space Station are floating around because they are freely falling to the surface of the Earth. In fact, not only is there gravity in space, there's quite a bit. Where the International Space Station orbits the Earth, the acceleration due to gravity is less, but it's about 8.5. 9.8 at the surface, 8.5 where the International Space Station is. Plenty of gravity. And the astronauts are freely falling. Oh no! What happens when the International Space Station crashes into the Earth? Well, it doesn't, because the International Space Station also has an extraordinarily large horizontal velocity. So as they fall toward the surface of the Earth freely, the Earth curves away. Orbiting the Earth is the art of throwing yourself at the Earth at extraordinarily high velocity and missing, going around in circular orbit, constantly falling, never crashing, in free fall and apparent weightless. Now another example of the application of Newton's second law, and the goal here is to continue to refine the process of solving the problems. So I have to begin with the drawing of the physical scenario I'd like to solve. Here I have a horizontal surface, and on it some sort of a crate is sitting there, and in principle it has a mass m associated with it. I'll have to specify numbers for all these. And I have Slim here, and Slim is going to drag this crate across the floor, and it'll be a little bit sophisticated because there'll be some friction involved. So he ties a rope to the crate and pulls the crate along. with the rope over his shoulder, as I've shown here in the diagram. And there's friction between the crate and the floor. Of course, there's the force of gravity, and the floor pushes upward on the crate. So there are a number of forces involved. And what I would like to do is the goal that I have for all Newton's second law problems that I solve. And that is, I would like to find the acceleration of the crate. But let me specify here some quantities for the start of my problem solution. Let's say that the mass of the crate is 10 kilograms, and hopefully I'll choose numbers that simplify my calculation. See what happens. So let's say the mass of the crate is 10 kilograms, and that Slim is capable of pulling with a tension force that is equal to 100 Newton. There's a friction force between the crate and the surface, but I haven't yet talked about how I can predict how much friction force I'll find in any given physical situation. And so I'm just going to make up a friction force here. I'll say that the friction force is equal to 20 newtons. It'd be perfectly appropriate for you to ask, well, how do you know that? We'll just have to imagine that I've done some experiment aside from this problem in order to know that. Slim is pulling the rope at an angle. So another thing that I need to know about this problem is what is the angle at which he holds the rope. I'm going to set that angle at 60 degrees relative to the horizontal. So I've drawn a picture of the physical scenario and I understand what's going on. The next step in problem solving is to choose coordinates. I have to choose what directions are positive. In the elevator problem, I just chose up as positive because the motion was up and down motion. There was really only one coordinate direction I need to worry about, so I chose upward to be positive. In this problem, I'll choose upward and over to be the positive directions. I need a positive direction not only for the vertical part of the problem, but also for the horizontal part of the problem. And the way I'll do that is I'll just draw this little icon here that says a plus and indicates that, it's the traditional math coordinates. To the right is positive and upward is positive. So any forces that point to the right are positive forces, and any forces that point to the left are negative forces. Any forces that point upward are positive forces. Any forces that point downward are negative forces. Picture drawn, coordinate system chosen. Now I have to draw a free body diagram for the object of interest. It's the acceleration of the crate that I'm trying to find. So I need to draw a free body diagram for the crate. That free body diagram will look like a box. Well, that makes sense because it is in fact a box, but my free body diagram is an abstraction of the thing whose motion I'm trying to describe. So here I draw a box and draw all of the forces that act on the box. In this case, does the box have weight? Yes. So I draw a vector directed downward. I label it mg. That is the weight of the box. Is anybody pushing or pulling on the box? Yes. Slim is pushing or pulling on the box. He's in fact pulling on the box with a rope. If I want to, I can call that a pull force and name it F. But he is specifically using a rope, so I'm going to call it tension T. It's just really important that I not call it both of those things. So I'm going to draw a tension force T that points off at an angle like that, indicates roughly the direction. Now that on my diagram looks sort of 45 degrees-ish. The angle I reported was about 60 degrees, so not drawn to scale, but it does give me the good indication that the tension is sort of off doing its own thing there. Any surfaces in contact? Yeah, the crate is sitting on the floor, and so there is a normal force perpendicular to the floor directed upward. Is there any friction force? Yeah, I actually mentioned the friction force is 20 newtons worth of friction force. And what direction should I draw it? Well, what direction I draw the friction force, I need to apply a little intuition to that. In this case, as the box is being dragged along the floor, the friction force is opposing the motion. So I'll draw the friction force vector in this direction opposite the direction of motion. And now I have a free body diagram that shows all of the forces that act on the crate in their appropriate directions, and I immediately see a problem. I know that my strategy is going to be to apply Newton's second law in the horizontal direction, that is along the x-axis, and to apply Newton's second law along the vertical direction, that is the y-axis. The tension force is not playing along. The weight force is a y-axis force, the normal force is a y-axis force, the friction force is an x-axis force, but the tension is a combination of both. It won't surprise you at all how I deal with that. I know that any vector quantity, like positions, velocities, accelerations, any vector quantity can be decomposed into its components. And that's exactly what I'm going to do. I'm going to leave the weight force and the normal force and the friction force alone. Here I redraw my free body diagram. With the weight force there and the normal force there, you might notice I drew it a little bit over to the side to make room for myself. The friction force that opposes the motion, directed that way. And now I'm going to draw the tension force on my free body diagram, not as the tension at an angle, but as its components. In order to learn the components, I have to resolve which component is which. I know that one component will be t cosine theta, and I know that the other component will be t sine theta. Well, here, the angle theta that I'm given is the angle between the tension force and the x-axis. What probably would be in the problem statement said at an angle theta with respect to the horizontal. As such, you can see that the component of the tension that would point along the x-axis is the component that would be adjacent to the angle. When I first talked about vectors, I said that the critical skill was to be able to identify that the adjacent component, or which component was the adjacent component, because the adjacent component is the cosine component. That means the component of the tension that points along the x-axis here is the tension multiplied by the cosine of the angle. Here, there's another component of the tension that points vertically, which is the tension multiplied by the sine of the angle. Once I use the cosine to find the adjacent component, the other component is the sine component. Now I have the most sophisticated looking free body diagram that I've drawn so far. By the way, if I were in the middle of actually solving problems, I probably would have skipped drawing this first free body diagram and gone straight for the one with the components. Because I know the very next thing that I'm going to do is to apply Newton's second law to the vertical and the horizontal coordinate directions. Typically what I like to do, and it's completely arbitrary, but I like to start with the vertical first. When we learn more about more sophisticated versions of problems like this, I think you'll begin to agree with me that writing the vertical equation is like the smartest and most efficient way to approach the problem. But I'll begin by applying Newton's second law to the vertical axis. That is, I'll write that the sum of all of the forces that act along the y-axis is equal to the mass multiplied by the acceleration along the y-axis. An interesting point here. Slim is dragging the crate along the floor, which means there is no y component to the velocity at any time. The crate is not going to rise up into the air. It's not going to dig down into the floor. There's no y motion at all. The y position, the y velocity, and so therefore the y acceleration remains zero the entire time. That means that the sum of the forces along the y-axis must be equal to zero. This is a state that we sometimes call force equilibrium. I might say that the vertical forces are in equilibrium. There is as much force going upward as there is going downward, and so there is no vertical acceleration. It turns out in this example I'm not going to learn much from this equation, but learning to write equations from the free body diagram is a valuable exercise, and so we'll go ahead and do it. In order to write the net force, I consult my free body diagram and consider only the forces that act along the y-axis. The normal force is a positive force. The tension sine theta is a positive force. The weight is a negative force. So when I write the sum of the forces, I'll lead with positive forces, which I like to do, and start with the normal force plus the tension times the sine of theta minus the weight force, mg, is equal to zero. As it happens in this example, that equation of motion for the vertical motion does not help me solve the problem at all. I want to learn what is the acceleration of the crate when Slim pulls it. I want to learn what is the acceleration of the crate, and this equation doesn't help me get that answer. But I do want to, and you know what, I'm going to put a box around it because it is the equation of motion for the vertical motion. And that is handy because it solves for the vertical motion no matter what the state of motion. At rest, accelerating, whatever. Well, I've set the acceleration equal to zero, so it's not that general, I suppose. I can learn a little thing from it, though, and it's an important point at this early stage of learning how to solve these types of problems. Just for fun, really quick, I'll do a little algebra and solve for the normal force. That is, the force of contact between the surface and the crate. And that would be mg minus t times the sine of theta. You see, I've just done a little algebraic manipulation. and solved for the normal force. You're going to solve a lot of problems where the normal force turns out to be equal to the weight. Very often, you'll be solving problems and N will be equal to mg. The point that one of 2 points that I want to make here is that the normal force is not always equal to mg. It depends on the context. Here's a context where the normal force is not, in fact, equal to mg. The normal force is not equal to the weight of the crate. The normal force often equals the weight of the crate because if I just set a crate on the floor here, it's the job of the floor to support the weight of the crate. How hard does the floor have to push upward on the crate to support it? Well, in principle, it's weight. So the normal force is often equal to the weight, but in this case, the normal force is equal to the weight minus some. It's equal to a number of newtons that's the weight of the crate, but a bit less. And the reason why is that when Slim pulls at an angle, there is a part of his pull force that is upward. And so Slim is helping the floor support the weight of the crate, and so the normal force can be less. It's important when we solve physics problems not to just treat them as math, but to think about what the equations say. Because when I read this equation, it says the force that the floor exerts upward is equal to the weight minus the force that Slim applies to help support that weight. And so the equation sort of speaks to me. But now the equation that'll solve the problem will be the sum of the forces, Newton's second law, applied to the x-axis direction. That is, the sum of all the forces along the x-axis is equal to the mass times the acceleration along the x-axis. The acceleration along the x-axis is not 0. The sum of all the forces along the x-axis is equal to the mass times the acceleration. I look at my free body diagram again, and I realize, ignoring the vertical forces now, that the only two x-axis forces that I have are the t cosine force, which is a positive force, and the friction force, which is a negative force. And so, all right, the net force is going to be t times the cosine of theta minus the friction force is equal to the mass times the acceleration. And I've dropped the subscript off the acceleration. I'm no longer writing ax, I'm simply writing a. Because there's only one acceleration in the problem, there's no chance for me to get confused. This is the equation of motion along the horizontal direction. It describes the behavior of the crate for any state of motion. At rest, constant velocity, positive acceleration, negative acceleration. This is the equation that solves for all motion. What I would like to do is find out, under these conditions where the mass of the crate is 10 kilograms, the tension in the rope is 100 newtons, the friction force is known to be 20 newtons, and the angle is 60 degrees. What is the acceleration of the crate? Well, now I've reached the plug and chug stage of the problem. So I'll just fill in the numbers as I go. The tension, I'm told, is 100 newtons of force that Slim exerts multiplied by the cosine of 60 degrees. And you see a little funny cheat that I did here in the problem to make things easy on myself. What is the cosine of 60 degrees? That's right, it's 1/2. Yeah, the cosine of 60, the sine of 30 is 1/2. The sine of 30 is 1/2. The cosine of 60 is 1/2. They're handy to know. It makes it quick to do a calculation. You'll find that sometimes writers of physics problems do you a favor and try and help you out with the head math. But if you're calculator obsessed, it's not really going to work out. So 100 times the cosine of 60 degrees, subtracting the 20 newtons of friction force. And you see, just a little bit of inside baseball here, that I had to be careful with my choice of the tension force that Slim exerts. I needed the component of the tension force in the direction of motion to be greater than the friction force. So as I stood over here, doing the problem, or making up the problem, I had to think about what choices I was making to make sure it worked out, and indeed it did. Because since the cosine of 60 degrees is 1/2, this works out to be 50 minus 20, and so I have 30 over here, the mass is 10, and divide, and I find, doing the algebra, a little bit uninteresting after all of the interesting physics that I've done, but the acceleration is 3 meters per second squared. So an application of Newton's second law to the problem gave me the answer that was the whole point of Newton's laws in the first place. Now that I know the acceleration of the crate, and by the way, I recognize that the acceleration of the crate is constant, then I can use my kinematic equations to predict the velocity position of the crate in the future, which is a rather remarkable achievement. Again, This problem has a certain level of sophistication. By adding different forces in greater multitudes under more unusual circumstances, I can create a problem where the equations of motion become more sophisticated and the math is more complicated. Nevertheless, the strategy for solving the problem is always the same. I draw a picture so that I understand physically what's going on, choose coordinates, draw a free body diagram showing all of the forces that can influence the motion and the directions in which they act. From that free body diagram, I write Newton's second law for my coordinate directions and then solve for the unknown one.